Hello and welcome back to CS300 Introduction to Algorithms. And we have been talking about a PhD thesis, the PhD thesis of Turing Award winner Stephen Cook, where he devised an entire family, infinitely many algorithms that include and generalize Katsuba's algorithm for polynomial multiplication, Toom's algorithm for polynomial multiplication, and far beyond that. And this is really, I promise you, it was admittedly complicated, mathematically involved, but this is the most difficult part of chapter 1 in this course, CS300. So please bear with me, be patient, and I'm going to explain it again from a different perspective. So here we are. What you see here is first the naive algorithm based on distributive law. Then there's a more involved algorithm based on Karatsuba's law. We never really spelled out the algorithm pseudocode or anything. The algorithms always occur here implicitly based on some recursive formula, mathematical formula that immediately leads to and induces a recursive algorithm. And then we would analyze that algorithm recursive cost. And in Karatsuba's case, it's 3 recursive calls to multiply polynomials of half the degree plus some linear overhead for the decomposition and recombination part. And you have solved that using the master theorem. And here you see on the current slide, you see Toom's algorithm. There's no algorithm, but you see again many mathematical formulas that lead to a recursive algorithm. In this case, the formulas involve polynomials of degree n over 3, so smaller degree in the recursive calls, but more recursive calls, but not as many as one might expect. One might expect naively 9 recursive calls, but here Toom gets away with 5 recursive calls. And here you see these 5 multiplications, all between polynomials of a degree n over 3. So having initially decomposed the original first problem into these 3 parts, thus decreasing the degree by a factor of 3, and also the second polynomial into 3 parts, and thus decreasing the degree by a factor of 3. And this saving in the number of multiplications, which is really the key to asymptotic efficiency, because addition I already know is optimal, takes linear time. We have algorithms for doing that in linear time, and that cannot be improved because the input is linear size and must at least be read. So addition is not really interesting, but multiplication here, our algorithms all take more time than the input and output size. Input size is kind of 2 times n, coefficient of polynomial a, coefficient of polynomial b. Output size is also roughly 2 times n, coefficients of the product polynomial is 2 times n. But the algorithms we've defined so far all have more than linear, more than constant times n computational cost. So, and that's why it's really the multiplication that is most costly, and that's where we're therefore put our emphasis, our interest in reducing the number of multiplications in the recursive calls at the expense of increasing other operations like the number of additions here, right? So in the naive distributive law approach, there's no addition here of the right argument, no addition here of the left argument. Here, Toom's algorithm has many additions, even scaling, right? Scaling also takes linear time, and that's optimal. So we don't really worry about the increasing cost induced by scaling or adding. And same here, lots of additions of intermediate results, but no additional multiplication here. So only 5 multiplication resulting in this factor of 5. And then you please apply the master theorem in order to determine the asymptotic growth of Toom's algorithm and observe that this is indeed asymptotically faster even than Karatsuba's algorithms. That's the improvement. And now we recall the Toom-Cook generalization of all these algorithms with a parameter, actually with 2 parameters. We want to be in full generality here. We consider 2 input polynomials A and B with 2 degree bounds, capital N, capital M. And we consider splitting the first one into small n parts, as you can see here, small n parts. And we consider splitting the second one into small m parts, as you see here. And then we devise an algorithm, a generic algorithm, using the paradigm, which is sometimes called evaluation interpolation outside. This goes beyond the purpose of this introductory course, so never mind about that. But the general idea again follows from a mathematical formula, and the mathematical formula you see here, which we've derived. It involves the inverse of a Vandermonde matrix, and since the parameters capital N and capital M are fixed, the cost for calculating the inverse of the Vandermonde matrix is not charged to the algorithm. The algorithm has the coefficients of the inverse Vandermonde matrix hard-coded by the programmer, that is by you or by me or whoever designs the algorithm, does so tailored for a certain value of capital N and tailored for a certain value of capital M to then construct the Vandermonde matrix with any choice of fixed numbers. Again, these are fixed as part of the algorithm design. One choice is, for example, minus n up to plus m integers, but this is just one possible choice. And then, the evaluation part is evaluate the first polynomial on these fixed numbers, which are now constant, and therefore the evaluation does not incur any multiplication, no, at least no recursive call when the polynomial A turns out to be a block polynomial, not the entire original polynomial. But in a minute, we're going to apply this formula, not to the entire original polynomial, but to a block, one of these small n blocks. And same here for the second part, for the B, where here the formula considers as B the entire polynomial. But when we want to multiply 2 blocks, then we just plug into this polynomial, into this expression, the corresponding block. So let's say B here is the second block and A is this block. Then evaluating this block here does not incur any multiplication, no recursive call, and neither does here. Only here, these dots, these multiplication, this is where recursive calls occur. And this is what we want to minimize. Okay, so right, and this is a mathematical formula for recovering the coefficients of the product polynomial. And if you could not follow and understand how this formula came up, that's perfectly fine, and you still can and are encouraged to follow up and simply take this formula as granted. Look at it, that this is a formula that provides the coefficients of the product polynomial using evaluating the first polynomial and evaluating the second polynomial at some fixed, arbitrary but fixed numbers, and then multiplying with this inverse Vandermonde matrix, which is that again constant and therefore hard-coded. Okay, and yes, I'm going to this is also explains the strange numbers that occur in both Karatsuba's algorithm and even worse in the Toom algorithm, which almost look like magical numbers, right? How did these numbers come? These numbers are the coefficients of the inverse of the Vandermonde matrix for suitable choices of these fixed constants. But if we choose the constant differently, then one gets another version which is similar, equivalent in a sense to Toom's algorithm, but with different constants. So this also Karatsuba's algorithm is not unique. There are actually many algorithms that have the same asymptotic running time as Karatsuba. There are many algorithms that have the same asymptotic time as Toom's algorithm, just using different constants, namely arising from different fundamental matrices, which are inverses arising from different choices of these numbers here. And right, and now for the recursive step. So this is where we apply this to the entire polynomial, but we want to apply this only to a block polynomial. So we replace the number capital K with a number small k, which is small n plus small m minus 1, namely the number of blocks that we have here, and how many evaluation and interpolation points are sufficient and necessary in order to recover the coefficients of the product polynomial of two of these smaller blocks, and then invoke a recursive algorithm in order to multiply the block polynomials in turn, right? So if this is a original polynomial, if this is a block polynomial, then evaluating that, the result will be a polynomial of smaller degree. And this leads to this recurrence, running time t of capital N to capital M degrees of the entire inputs is equal to n plus m minus 1. This is the k here, depending on the number of blocks that we want to divide here, times that many recursive calls to polynomials of degree reduced by a factor of small n and factor of small m here, plus the overhead for the division and for the recombination phase, which is quadratic, very costly in terms of this number of blocks, but the number of blocks again will be fixed. And we've recovered this. We've seen when small n and small m are both 2, then this is a factor of 3, and then we recover Karatsuba's algorithm. If we choose in Cook's algorithm small n equal to 3 and small m equal to 3, then this is a factor of 5, and we recover Toom's algorithm. And if we choose small n and small m other, possibly larger, then we obtain a different algorithm, which is asymptotically even faster, but asymptotically because there's a larger constant hidden here. So depending on when n and m is sufficiently large, such that the asymptotic has a chance for kicking in, then this is good. But when n and m are not so large, then actually the constant that we have been ignoring dominates the running time, and we're not in the asymptotic part. Right. There's a great question in the chat. Where does the recovery appear in Toom and Cook algorithm? Yes, this is kind of after having all these multiplications, then we have the results, and we have overlapping polynomials that still need to be added. Maybe this is best illustrated by recalling the Karatsuba algorithm here. Right. Remember this one here, where we had in the recovery, we would need to add polynomials that would shifted polynomials that would overlap, like the middle part would overlap both here and here. And a similar thing appears in Cook's algorithm, but it's even more involved and not nice to illustrate. So I chose to not put it on the slides. So that being said, and now we're moving on to the final topic of chapter 1 of CS300, namely matrix multiplication, is another great example of algorithm design and analysis. So, you know, matrix addition, where the input is, let's say, 2 n times n matrices A and B. So the input is n squared entries And let's say our algorithm is allowed to use only arithmetic operations, multiplications, additions, and let's say also subtractions and scaling. And we count the number of arithmetic operations to make the problem well specified according to our virtue. And we're interested in outputting the entries of the sum matrix for now. Let's start with the sum. Then that algorithm is easy, right? Just component-wise addition, which has quadratic running time, and that's optimal because the input has that size and the output has that size, so there's no way to get below n squared for addition, which is the same situation as we had with polynomial addition. We have linear time as optimal. Things start to get interesting when we talk about multiplication, as was in the polynomial case. And again, we have here our standard algorithm that you all know from linear algebra, which has a cubic running time. So taking a row times column takes linearly n many additions and n multiplications, row times column, right? And doing that for any n squared possible entries in the result yields another factor of n squared, making n cubic running time. And the question is this naive school algorithm optimal or not? And it turned out, quite to the surprise of many scientists at that time, that it is not optimal. And to see this, we're going to devise, again, a recursive algorithm first, the same recursive algorithm that is also in the classical school method of linear algebra, namely by, yes, I will explain why it's cubic in just a second again. Thanks for this question. But let's first consider a recursive algorithm, right? So we subdivide the given matrix A into blocks of half the size. So now each entry is in turn a matrix, and same for B. And then we naively multiply this with this with row times column, right? This times this, and this times this, and add the both to get this element. So that's two multiplications to get this one. Then row times column, one multiplication, another multiplication to get this entry, another two multiplications. So that means a total of 8 multiplications in the recursive, 8 recursive calls to multiply matrices of half the size, namely each of the blocks. That's our recursive algorithm. And if you solve that recurrence, 8 recursive calls to matrices of half the size, that gives also cubic running time, the same running time as the naive algorithm by taking just regular row times column. But here's a more efficient algorithm, mainly again with lots of more involved mathematical formula. But the point here is, here we get away with 7 multiplication. 1, 2, 3, 4, 5, 6, 7 multiplications of matrices of half the size, right? So this seems very similar to Karatsuba's algorithm, first taking some linear combinations of the blocks. Karatsuba took linear combinations of the blocks of the polynomial decomposition. Here we take linear combinations of the blocks of the block matrices, and then in a smart way, using only 7 multiplications of these linear combinations, and then performing more linear combinations of the results to recover the entries of the resulting matrix. And again, observe that these are all block matrices, the intermediate results, but this immediately leads to a recursive algorithm, right? You can see how this happens. And the recurrence here with 7 multiplications and many linear combinations, but again, linear combinations are not costly asymptotically. Matrices of half the size gives rise to this recurrence. The cost of our recursive new algorithm is 7 times the cost of multiplying matrices of half the size plus 18 times this quadratic cost for the linear combination, and that's asymptotically. Yes, please apply the master's theorem yourself. That's n to the binary logarithm of 7, which is roughly 2.82, and therefore less than n to the 3, less than cubic, right? So this algorithm has improved from cubic running time to subcubic running time. So again, an example of an improved algorithm, which again raises the question, is this optimal? Is this the end of the story? Is this the best algorithm? And yes, the question is asked in the chat, why there are there 18 linear combinations? Please count them yourself. Also, it doesn't really matter if it's 18 or 15 or 50, because this is a constant that is going to be ignored asymptotically anyway. The question is valid, but I don't want to go into detail here and leave it to you to do the counting. Thank you. The message here is that, yes, this historically was the starting point of a sequence of better and better algorithms, of sequence of improvements. And the current world record is held by François Le Gall at Kyoto University from 2013 with a running time of n to the 2.37 and several more digits. So each better algorithm historically gave a little bit of improvement, epsilon improvement, and less digits, like with running 100-meter competition. Usain Bolt was only a little bit, some hundreds of seconds faster than the previous world record, and thus he beat the previous one, and now Usain Bolt is holding the world record. The same holds here from François Le Gall. And the question still stands, is this optimal? Most likely not. If you just look at the number, there's nothing natural or canonical about the number 2.37. It's just probably an artifact. So if you want to become famous, why not try to devise a more efficient algorithm for matrix multiplication that uses here? These are all recursive algorithms, every single one, also François Le Gall's algorithm. Try to devise one that uses less than n to the 2.37 asymptotic cost. So there's a question in the chat. What are T1, T2, T3, and T7? These are the kind of intermediate results of the recursive algorithm, right? So the recursive algorithm that you don't see here spelled out calculates the sum of these two block matrices, then makes a recursive call to multiply that to this other block matrix of half the size, and store that in this temporary variable. And same here, 7 recursive calls whose results are stored in temporary variables, and then these temporary variables are added and subtracted and combined in a smart way. Again, where do the constants come from? That's the magic here. And so far, nobody has been able to find a counterpart to Cook's algorithm that generalizes all these algorithms. All these algorithms still are really tailored. And you see, for example, T1 occurring here 2 times, T4 occurring 2 times. So that's kind of where maybe one point where the saving really comes in, that all these intermediate results are used several times without incurring further multiplications. And when we calculate the cost, I said we focus on the multiplications. We don't really ignore the additions and multiplications, but our focus is on the multiplication, because this is what determines the asymptotic cost. That was what determines the exponent, whereas the number of additions and multiplications, like this number 18 here, determines the constant here, maybe much larger than 18, but still it's a constant that we're going to drop. So that's not really where our focus should lie? Thank you for that great question. And another great question, what if the matrix has an odd size? Excellent, thank you so much. We had a similar discussion when we divided the polynomials. And with the polynomials, it had no loss of generality to suppose that the matrix dimension is even, because if it is odd, then we can just artificially enlarge the matrix with a 0 row and a 0 column. That doesn't change the result of the multiplication, right? And thus arrive at the matrix which is only a little bit larger asymptotically. Only again, this doesn't make any difference, but now has even size, and we can apply the recursive subdivision approach. Thank you very much for that good question. Okay, so that being said, let's now recap chapter 1, Introduction to Algorithms. We talked about computational problems and algorithmic solutions via the virtues of computer science: specification, semantics, algorithm design, efficiency analysis, optimality of algorithms. If they're not optimal, start over again with a better algorithm design, better analysis. And we've discussed this at the example of repeated squaring, where our first algorithm had linear cost, and then repeated squaring had logarithmic cost, and then we proved that logarithmic cost is optimal. And then we would apply that algorithm when we to one of the algorithms for computing Fibonacci numbers. First, the recursive algorithm, which had exponential cost, then the iterative algorithm, which had polynomial cost, then the algorithm based on matrix powering using recurring sparing, which had a logarithmic number of operation, but still a linear, superlinear bit cost. And finally, two algorithms based on Binet's formula that would use stronger and stronger primitives of irrational and even of transcendental numbers. And we talked about recurrences and master theorem to solve these recurrences asymptotically. And finally, we talked about algorithm for polynomial multiplication, long multiplication, Karatsuba, Toom, and a family of Cook, Stephen Cook, and finally matrix multiplication, where the complexity, the optimality is still unknown. So that's all from chapter 1, and unfortunately I have to stop the lecture this time due to another meeting. So we'll catch up on the time later, make up a lecture extension later. So thank you very much for your attention for now, and see you next time.